what lies beyond the universe? If you're ready for an absolute cosmic identity crisis, then join me on a journey through space and time to the edge of the cosmos. Be sure to stick around until the very end, and let's get started right away. We assume that space began 13.8 billion years ago with the Big Bang and has been expanding ever since. But if that's the case, what was there before the Big Bang and what lies beyond the universe? There are some answers to the questions of what lies beyond the cosmos and what existed before the Big Bang. So let's take a look at them. The cosmos was born, starting out very small and then growing larger and larger until today. This is called cosmic expansion. That is the Big Bang theory, but to this day it has been difficult to prove conclusively. However, all the evidence points in its favor, and among cosmologists, this theory is the overwhelmingly dominant view. After all, we can observe beyond a doubt that the cosmos is currently expanding and that the vast majority of galaxies are moving away from one another. But where exactly is the edge? Or is the universe infinite after all, and into what is it expanding? Let's first clarify whether the universe even has an edge, and then we'll see if we can observe it. The problem with our conception of the universe is that we are three-dimensional beings, so we always imagine the expanding universe as something like a soccer ball that keeps getting inflated. But the universe has at least 4 dimensions. Some cosmologists even assume there are more than 10 dimensions, and that simply exceeds our cave dwellers' understanding. One possibility, however, is to view the universe as a finite curved surface. Our universe isn't a three-dimensional structure, but a multi-dimensional space-time balloon. Therefore, even though it's finite, it could lack a visible edge. Some cosmologists have fleshed out this idea a bit and concluded that the universe is more likely to be a donut. This concept of a multi-dimensional donut is also called a Poincaré donut, named after the French mathematician Henri Donut. Henri Poincaré. The idea behind the theory is that the universe could be curved in such a way that it folds back onto itself, similar to the surface of a donut. Space, then, wouldn't simply be flat and expansive, but would curve in a way that's rooted in higher dimensions. It would have a finite extent, but this boundary would exist in a way that would be almost impossible for us three-dimensional beings to grasp. This theory seems very realistic based on certain observations. To test whether the cosmos is a donut, one could check to see if it repeats itself at certain points. Unfortunately, it would probably take quite a long time to run through the entire universe, and most scientists aren't up for that. That's why they use telescopes to search the cosmos for recurring patterns. Unfortunately, in this gigantic universe, that's even more difficult than the famous search for a needle in a haystack. But conveniently, we can look back to a time when the universe was still very small. That's because every glance at the sky is a glimpse back in time. You see these objects as they appeared when the light set out on its journey. Astrophysicists can look back to a time when the universe was only a few 100,000 years old. About 380,000 years ago, the universe became transparent. This means that radiation, more specifically cosmic microwave background radiation, was suddenly emitted. We can look back to that moment and see a gigantic, all-encompassing wall of cosmic background radiation. Since the universe was much smaller back then than it is today, it is much more practical for cosmologists to examine this cosmic background radiation for recurring patterns. And that is exactly what a research team led by Thomas Buchert from the University of Lyon did, and they arrived at truly surprising results. They examined the cosmic background radiation primarily for temperature irregularities. The hypothesis was that if one or more dimensions in our universe were to reconnect with themselves in a donut-like fashion, these irregularities could not be larger than the distance between the points where the universe would have to reconnect. To put it simply, one could say that there would have to be fewer irregularities in the temperature distribution of the cosmos, for example, if it repeated in a ring-like pattern at multiple points. And indeed, the investigations by Thomas Buchert and his team showed exactly that. So let's work with the donut universe hypothesis for a moment. The donut has an edge, so we should be able to see it somehow, right? Unfortunately, not really, because that edge would likely lie beyond our observable horizon. The observable horizon is the maximum distance that light has been able to travel since the Big Bang, and that we can therefore see from Earth using telescopes. Everything beyond this observable horizon is invisible to us since the light hasn't had enough time to reach us yet. It's very likely that the light from the edge won't reach Earth even in the distant future, because the cosmos doesn't play by its own rules. On large scales, it expands faster than the speed of light. Incidentally, this wouldn't make Einstein turn in his grave, because he wouldn't have minded. His cosmic speed limit applies only to the motion of physical objects through space, from one point in the universe to another. In general, the expansion of space has nothing to do with the motion of objects in space and is in no way limited by the speed of light. This means that information from the edge of the cosmos will never reach us because it moves more slowly than the cosmos is expanding. An obvious answer to the question of what lies beyond the cosmos would be that there is another universe beyond it, and then perhaps another and another. But let's rewind very briefly. The name Big Bang Theory was coined by the theory's critics to ridicule it. In the early 20th century, the Belgian physicist and priest Georges Lemaitre proposed the theory of an expanding universe that began with a singular event, and he called the whole thing the primordial atom. But since the entire physics community at the time, including Albert Einstein by the way, assumed a static universe that wasn't expanding, everyone thought Lemaitre's idea was silly and wanted to discredit him with the term Big Bang. And of course, there are many unanswered questions, especially what was there before the Big Bang and how will the cosmos end? Naturally, that's a bit difficult to figure out, but what researchers have discovered in this regard will blow your mind, I promise. The research began with a hypothesis, one proposed by the famous mathematician and physicist Roger Penrose. He developed a cosmological model called Cyclic conformal cosmology, or CCC for short. Essentially, he uses it to describe a cyclic universe. That is, a universe that never ends because it keeps starting over from the beginning. The idea itself isn't new. You've surely heard of the Big Bounce, the cosmological theory that states our universe will continue to expand until it eventually begins to contract and returns to a tiny singularity. But Penrose's CCC theory is a little different. It doesn't include a cosmic contraction process. He envisions the whole thing as follows. The universe grows and grows and grows until, at some point, it is so vast that all the stars have long since died and even the last black holes have evaporated due to what's known as Hawking radiation. Everything that has ever existed has dissolved in this ultimate final stage, and the distances are so vast that even the concept of space-time becomes obsolete. The universe is then nothing more than a featureless, indefinable blob. At this stage, the conditions are now in place to initiate a new cosmos. Penrose's idea, therefore, is a cyclic universe that never shrinks but only grows, and this fits perfectly with the observations we are currently making about the cosmos. For it has been determined that the expansion of the cosmos is not slowing down, but continues to accelerate. Researchers have even been able to find evidence supporting Penrose's idea. This evidence takes the form of swirling polarization patterns known as B-modes in the cosmic microwave background. In the cosmic microwave background, we see variations in radiation and temperature from the earliest universe, and perhaps even imprints from the predecessor universe. The B-modes are in effect remnants of black holes from a dead universe. Specifically, there are 20 such B-modes that were collected in 2014 by a microwave sensor called BIZEP2, which is located in Antarctica. Penrose assumes that these anomalies in the cosmic microwave background are so-called Hawking points. In space, pairs of particles and antiparticles are constantly being created. When they meet, they annihilate each other. But what if such a particle-antiparticle pair is created right on the boundary of the black hole, beyond which nothing can escape, the so-called event horizon? In that case, it can happen that the particle ends up on the safe side outside the event horizon, but the antiparticle was created on the wrong side and is now violently sucked into the center of the black hole. However, an antiparticle has negative energy. As a result, the mass of the black hole decreases. This process of evaporation via Hawking radiation takes an eternity. But if one could observe and record a black hole for billions of years, the cumulative effect of Hawking radiation would become clearly detectable. That would then be a Hawking point, and perhaps the black holes from the previous universe left their Hawking points behind in the cosmic microwave background radiation. That is precisely Penrose's idea, that the after effects of black hole evaporation outlast the death of one universe, radiate into the new one, and are then reflected as an artifact in the cosmic microwave background. I don't know about you, but I find this mind-boggling. Feel free to share your ideas and thoughts on the topic in the comments. I'm really curious to hear what you think. If another universe were to actually exist alongside our own, the question arises as to how they would be connected. Some researchers believe that our universe exists inside a black hole. This has to do with the characteristic properties of a black hole. Black holes are simply incredibly dense and massive objects whose gravitational pull is so strong that they even suck in light. Everything is then sucked toward the center of the black hole, and at the center lies what's known as a singularity. A singularity isn't even a millimeter in size, but it's incredibly dense. As you can see, the whole thing closely resembles the description of the Big Bang. A huge amount of matter compressed into a tiny little point. And these similarities have led astrophysicist Nikodym Poplavsky from the University of New Haven to propose the theory that our universe exists inside a black hole. It sounds totally crazy, but the more you think about it, the more sense it somehow makes. But how does the singularity suddenly begin to expand? Nikodym Poplavsky compares the whole thing to a plant seed. A plant seed already contains everything needed for the fully grown plant. It just needs the right conditions to start germinating. And a singularity is, so to speak, the seed for an entire universe. Due to the black hole's rotational speed, extreme forces act on the singularity, which could eventually cause it to simply go pop. And just like that, we have a Big Bang. Of course, this couldn't happen in every black hole. It depends much more on how much mass a singularity already possesses. But of course, the whole thing is just speculation. No one knows if it's true. And it must be said that mainstream scientists actually all reject this. But this hypothesis that we live inside a black hole would explain a number of mysteries. For example, it could explain why the Big Bang happened in the first place. If that were the case, there would essentially be a mother universe for us containing the black hole that leads to our universe. It could also answer the question of what lies outside the universe, namely the black hole itself and at some point the event horizon. This would also explain why we can't detect any interaction between our universe and another universe. After all, the event horizon doesn't let any information escape. So we would be isolated from our parent universe by the event horizon of the black hole in which we find ourselves, which would explain why we can't see beyond the universe. But there are also a few slightly more imaginative theories about what the universe as a whole looks like and how it might interact with the space around it. One of them has to do with the Gaia hypothesis, which essentially states that our Earth could be a single organism. But what if even the entire universe were alive? We can define living beings as organized genetic units capable of metabolism, reproduction, responsiveness, growth, and evolution. However, there are also borderline cases, such as viruses, which are generally not considered living beings since they are not capable of reproducing on their own and do not possess metabolism in the strict sense. And it gets even more complicated when we consider that each of us, in turn, consists of countless smaller living beings. All the bacteria in your body, without which you wouldn't function as an organism, are after all individual tiny living beings. So if we are living beings that in turn consist of an infinite number of smaller units, then the idea that larger units could also be living beings isn't so far-fetched after all. Take the Earth, for example. This idea is known as the Gaia hypothesis, and if we take it a step further, the entire cosmos could be alive. One argument that could be made for viewing space as an organism is evolution. Cosmology describes the development of the universe, starting with the Big Bang as its beginning, continuing to the present day and extending into the future. The universe is expanding. Within it, elements, stars, and finally galaxies formed. All of this already seems relatively alive. Classical evolution of living beings, on the other hand, refers to the changes that species undergo over time. This includes adaptation to their environment and changes in their genetic material. At first glance, this sounds quite comparable, but upon closer inspection, the analogy falls apart. This is because the processes in the cosmos are based on the fundamental laws of physics and the behavior of matter and energy in the universe. These can therefore be described directly in physical terms. The evolutionary processes on Earth, on the other hand, follow biological laws. The situation is similar with another aspect, self-regulation. One could say that both living beings and the universe regulate themselves in a certain way. Self-regulation means that a system can respond to changes in a specific way to maintain or restore a certain state or function. Our bodies, for example, constantly strive to keep our body temperature constant, for instance by sweating. Does the universe sweat too? If the universe sweats, I'd say the cosmic sweat consists of hydrogen and new stars form from it. And the rate at which new stars form in a galaxy seems to be fairly constant. In the Milky Way, that's about 5 solar masses per year. So are we dealing with a process of cosmic self-regulation here? Here too, upon closer inspection, this view is probably not tenable. We know that in individual galaxies, star formation can suddenly surge. For example, when 2 galaxies merge, causing gigantic hydrogen clouds to collide. There's no evidence to suggest that this is then balanced out elsewhere in the universe, such as by thousands of stars in another galaxy suddenly ending their lives in supernovae. Of course, one could argue that the total potential of energy and mass in the universe remains constant. That is, after all, what the laws of thermodynamics state. But in my opinion, that is not sufficient to assume biological self-regulation here. The fundamental laws of physics and the interaction of matter and energy in the universe create a cosmic system, but not an organic one, I would say. One argument against the thesis that the universe is alive is above all the lack of any discernible purpose or intention in its existence. Living organisms have the purpose of reproduction, and in the case of Homo sapiens, of course, all sorts of other self-imposed, immensely important life purposes come into play, such as sitting in an open-plan office for 40 hours a week. But given our limited knowledge, we probably can't presume to know the purpose of the universe just yet. One point that's very important to me here, however, is that we might be a tool of the universe, created by chance to give meaning to the whole. That's an incomprehensible, precious privilege that makes me very, very happy to be alive. But there are other obvious theories about our universe. When you look at the microcosm, that is the tiniest structures, and the macrocosm, the largest structures, you often find that many structures are very similar. This is what we call fractals. A fractal is defined as a structure in which, if you zoom in far enough, you eventually encounter a pattern that repeats the original pattern observed on larger scales. When similar patterns repeatedly appear on increasingly smaller scales, we can analyze them mathematically to determine whether they exhibit the same statistical characteristics as the larger structures. The mathematician Benoit Mandelbrot was the first to recognize the principle of fractals. Mandelbrot was quite obsessed with fractals and even believed that stock market prices could be predicted and analyzed using fractals. Not least, he thought it possible that our entire universe is a fractal. That was in 1974, and at that time, astronomers had only just begun compiling extensive catalogs of galaxies from the depths of space, and initial concepts of the large-scale structure of the cosmos were beginning to take shape. Today we have a pretty good picture of what the very large structures of the universe look like. We've already talked about the cosmic microwave background today. It consists of filaments and voids. The filaments are the bright strands around which almost all the matter in existence is concentrated. Almost all galaxies, such as our Milky Way, are arranged within these gigantic cosmic filaments. But in between them lie unimaginably vast voids. Here, a yawning emptiness prevails over unimaginable distances of hundreds of millions of light years. Surprisingly, a detailed analysis of the voids actually reveals the same structure. The few solitary galaxies drifting through the voids form a sort of mini cosmic web, so the filament structure has repeated itself at least on one level. It is therefore similar to itself in at least some ways, but one level isn't really that much, is it? And at smaller scales, the fractal structure of the universe no longer holds up. Our solar system alone looks completely different from any other star system. So if at all, the universe can only be fractal at the very largest scales, and even there, the evidence is slim. Some structures at the very small and very large scales may resemble each other in part, but that alone doesn't make a fractal, because for that, we'd need self-similarity across multiple continuous scales, not just on one very, very large scale, and then by chance on a completely different scale under a microscope. The reason why such vastly different structures resemble one another isn't entirely clear, and even if it's a bit unsatisfying, it could simply be a coincidence. And ultimately, both the microcosm and the macrocosm are governed by the same laws of nature, and some arrangements and patterns probably just make sense according to those laws. There may still be one last option, the multiverse. We just looked to see if we could find a fractal pattern by zooming in from the cosmic web, the largest known structure, to smaller structures, and we were bitterly disappointed. But what would we see if we zoomed out from the cosmic web? What lies beyond it? Some researchers assume that our universe is not the only one. There could be another universe above or beside our own, perhaps even a parent universe and then a grandparent universe. So it's conceivable that an even more immense structure, similar to the cosmic web itself, might appear above it. A multiverse fractal, because if new universes are constantly emerging, then we would truly be living in a kind of cosmic Mandelbrot set. Sometimes I find myself thinking that perhaps our human problem is simply that we can't imagine nothing. So maybe we just need to solve the mystery of nothing. When we try to think of nothing, it just doesn't work out. Even though it feels like a lot of people are really trying hard to think of nothing, many would probably think of a vast black void. But first of all, we'd realize that even seemingly empty space is usually not a perfect vacuum. Even in the particularly empty regions of the cosmos between galaxies, there is what's called intergalactic matter. Now we could suck the hydrogen and dust out of our little empty space. Then we'd have a perfect vacuum of nothing. Removing the matter would mean that energy would remain. Just as the sun's energy can travel through empty space to Earth, heat would radiate into our vacuum from other parts of the cosmos, so the space would still not be empty, but we can solve that too. We simply cool the space down to the lowest possible temperature, absolute zero, so that it no longer emits any energy at all. We also build walls, so that no energy or radiation can penetrate from the outside. Then there would be absolutely nothing inside the cosmic box, right? Wrong. Unfortunately, quantum physics throws a wrench in our plans here, the branch of physics that deals with processes at the tiniest scales and that often contradicts our apparent reality. Even in such a seemingly perfect vacuum, tiny subatomic particles keep popping up and disappearing again, quantum foam. One of the most confusing of all quantum principles, and they're all confusing, is Heisenberg's uncertainty principle. You cannot simultaneously measure the position and momentum of a subatomic particle with perfect precision. Subatomic particles cannot be precisely determined in terms of two measurement parameters at the same time. The principle also states that one cannot perfectly measure the energy of something, and that the shorter the time interval being measured, the less accurate the measurement becomes. But what does all this have to do with our search for nothingness? If we simply try to measure the amount of energy in our cosmic vacuum chamber, even if that energy is supposedly zero, we still cannot measure exactly zero due to the uncertainty principle, and that is a quantum physical property of reality. For short time intervals, the 0 point is not always zero. Heisenberg precludes the existence of nothingness, and Einstein also has a say in the matter. Einstein's famous equation, E equals mc squared, states that energy is matter and vice versa. In conjunction with quantum theory, this means that space in a location that is supposedly completely empty and devoid of energy can briefly fluctuate to an energy value other than zero. And this temporary energy can turn matter into particles. So the apparent nothingness in seemingly empty space is never nothing. The supposed nothingness is much more like a pulsating place where tiny subatomic particles appear and disappear again, which also means that our entire existence is a bath in quantum foam, so nothing is not nothing. I don't know about you, but my head is really buzzing. Probably because it's full of quantum foam. I know, today's episode was pretty intense, but I hope I was able to give you a few more perspectives on what might be out there beyond our universe. I'll keep you updated on any new findings, but of course that's only possible if you subscribe to my channel. From the YouTube stats, I know that over half of the viewers aren't subscribed, and it's absolutely free. You'll never miss another galactic video, and you'll be helping me out a lot. So everyone, go ahead and hit that subscribe button. Thank you so much. And for anyone who's still craving more astrophysics, there might be a black hole inside our sun. It's called a Hawking star, and scientists have discovered some truly mind-blowing things about it. To find out whether our sun harbors such a gravitational monster and whether we'll soon be spaghettified, be sure to click on the video below. As always, you'll find another topic related to space and science in the bottom right corner. Otherwise, I'd say see you in the next video. That is, if you haven't fallen out of the universe by then. Take care, everyone.